My name is Laura Alford. This video is going to be about subdivision and floodable
Subdivision and floodable length to follow along with what we were talking about with the flooding of a ship. If your ship has become damaged, it has flooded, what are you going to do about it? Obviously, we would like to try and restrict the flooding effects as much as possible. We can use watertight bulkheads to divide up the spaces in the ship and contain the flooding to the minimum possible number of spaces. One way to calculate how many watertight spaces you need to have is by calculating the floodable length of the ship. So, first some terminology. Here's a little cross-section of a ship. You have watertight bulkheads, which are just walls that are watertight, right? No water can get through. These lead up to a bulkhead deck, which is also watertight. You might recall that this was the Titanic's problem. It had the watertight bulkheads, but not the bulkhead deck, so water was able to spill from one space into another. We no longer have that problem. If the ship is damaged, water will come in, it will flood, but flooding is restricted because of the watertight bulkheads and the bulkhead deck. But the question is, how many watertight bulkheads do you need? We can appreciate that probably more of them is good, but then it makes it hard and expensive to make the ship. Sometimes you need to have larger spaces because of cargo holds, so you need to figure out exactly how many you need to have. One way to do this is to use floodable length. So, floodable length is kind of a weird concept, so I've got some pictures here that hopefully will help make sense. In general, the floodable length is the length of the ship that, when it's flooded, will cause the ship to sink and trim such that the margin line is immersed in the water. The margin line is an imaginary line. It is a minimum of 3 inches below the bulkhead deck. And what it means is it's like a bulkhead deck with the factor of safety put on top of it. So if the margin line is submerged, it says that's the maximum amount of flooding that the ship can handle before it sinks. A couple of assumptions. The flooding is assumed to be beam to beam. That means it goes from one side of the ship all the way to the other. And also that floodable length is centered at the middle part of the entire floodable length, so like at point A here. Okay. You can do this analysis from one end of the ship all the way down to the other. So here I've got something started at the bow of the ship, right? The ship has flooded such that the margin line has been immersed. And for this illustration, I'm not including the effects of trim, though when you're calculating it, you do. I just don't have it in with these cartoons because it'll get all complicated. So what you do is you have the floodable length. It is so much, and that will cause the margin line, like I said, to be immersed. You can take that floodable length and also plot it vertically. It's the same scale, and put that little dot there, right here. Okay, you can take this and then do the same thing all the way down the entire length of the ship. And you can see that it changes because the geometry of the ship changes. So you fly along all the way down here and say, voila. If you connect the dots, you get the floodable length curve. And you can see that there are some regions of some shorter floodable lengths. This is because the ship trims, right? So if there's a bunch of flooding up in the bow, the ship will trim, bow down, and that will immerse the margin line faster. Similar with the stern, right? If the stern starts to dip down, that margin line is going to get immersed much sooner. In the middle, because the ship will sink in parallel, it will sink evenly, the floodable lengths are actually a little bit higher. And then relatively speaking, there's longer floodable lengths at either end. This is because the bow and the stern of the ship are narrower than the middle part of the ship, the mid-body. It really goes back to a calculation involving volume, right? So if you have length times width, well, if your width is much less, then you can get away with a longer length. Okay, so the floodable length curve. Remember that the floodable lengths are centered around the midpoints of the flooding, okay, right here. You can take that then and you can draw these little triangles here, and these will come into play in a little bit. But generally speaking, then you draw floodable lengths, connect them with triangles here. And then this, once you clean it all up, this is the floodable length for a given permeability. And this is the traditional way that you would see a floodable length curve with these diagonal lines, then how it changes, and then going back down to the bow and the stern there. You can take that floodable length and you can do it for different permeabilities for those spaces. And you can either do it for, as I've shown here, where it's one permeability for the going down the whole length of the ship. You can even do it piecemeal. Right? Like if you know these different spaces have permeability of 0.9 or 0.8 or 0.7, you can do it in little bits and pieces. I've seen it both ways. So what is the point of all of that? You can use the floodable length to test your bulkhead locations. This is what you do. So you take a ship, you've chosen some bulkhead locations, you want to evaluate them to make sure that it's going to be sufficient to have contain flooding for your ship. Okay. So you take the ship, overlay the floodable length curve. So remember, the floodable length curve is the allowable flooding that can happen for the ship before it sinks for a given permeability. You take that, draw these little floodable length triangles for each one of these compartments. And this is kind of a confusing diagram at first. Look at it a few times, come back and watch the video again if you need to. It will start to make sense. But what it really is it's floodable lengths for each of these compartments, and it's not continuous, sort of like the original one was, right? Because you restricted the flooding because of the bulkheads that you placed in there. So you draw the triangles for each compartment and each pair of compartments. And then you can trace over them. You can trace the actual floodable length for the one compartment flooding, that's the lower teal line, and then you can trace the actual floodable lengths for the two compartment flooding, that's the purple line. Okay? You compare the actual floodable lengths, those highlighted lines, to the allowable floodable length, which is the red line. Okay? For this case, because the purple line is completely underneath the red line, it means that this is a two-compartment ship. It means that any single bulkhead can be damaged, can be taken out, and the ship will not sink. That's a good thing. Here's another example. Same ship, but now we have fewer bulkheads, so we have larger compartments. We'll overlay it with its floodable length curve here, this different permeability. We take it, again, draw the floodable length triangles for each compartment and pair of compartments. But now we have less bulkheads, we have larger spaces, and so the triangles are correspondingly larger. We do the same thing, highlight the lines for the actual floodable lengths for the one compartment flooding and for the two compartment flooding, and we see, this part of the two compartments triangles is above the floodable length curve. The one compartment triangle is all underneath this, so that's okay, but that little part is above the allowable floodable length curve. So what it means is that if this bulkhead is damaged, these two compartments are going to flood and the ship is going to sink. So this is only one compartment ship. So you can appreciate, right, that a two-compartment ship is safer than a one-compartment ship. A three-compartment ship is probably safer than a two-compartment ship. But eventually, you could put in so many watertight bulkheads that, any damage at all causes 5 of them to flood, and so it sort of defeats the purpose. So this calculation with the floodable length, and there's also a factor of subdivision, which is kind of like a safety factor, is an older way of doing it. And you can still do it, and it's actually not a bad way of just sort of checking things, right? Okay, does this make sense? But it can't capture a lot of things about ships that happen, that we know happen. So the new way that we do things is really with a probabilistic damage assessment, and this is actually fairly involved, so this will be in the next video that we'll go through it. But the floodable length, it gives a good basis for understanding how flooding works, and how to contain it, and it gives you maybe a good starting point, because it's pretty simple. You can write up a little spreadsheet for it. And then from that, you can go through and start to look at probabilistic damage assessment of your ship. So, thanks as always for your time, and see you next time.